Yeah, we call this small and large cheese facility. You will see in the presentation a lot of parameters are actually the same, but there is some particularity with large facilities. So that's why we made this distinction. So geographic location, small introduction. When you choose to make a food plant, it's very important to maybe choose an area which is away from odor, a place where there are bad odors, smokes, dust, or a food-prone zone. Pathways and hallways must be designed to easily be washed and sanitized. We need to keep an hygienic environment in our facility. There is different in the talking about dairy. There is different, of course, areas in a food processing plant. We'll be focused in the red square here, talking about ressuage, which is a kind of a surface drying, ripening, and drying. Critical construction points. You have to make sure to use non-absorbent and chemical-resistant material. These parameters here are valid for the air treatment, but also for the walls, for the floor, the ceiling, a good draining system, pitches that can be on the floor also, that can be in the equipment. We don't want any water retention because where there is water retention, there is bacteria growth and molds. Good accessibility. If it's accessible, it's easy to wash. Minimal occurrence of dead zones. Again, a dead zone is somewhere where we can't access, so it's a bacterial growth potential. For the equipment, the standard is to use stainless steel, of course, 304 or 316 L when it's there is a salting process or brine. It's resistant to aggressive ambience and detergent. So trying to segregate a bit what is a small cave, a medium cave, or a large cave, just to give some ideas. Something below 20 square meter will be considered quite a small cave, 20 to 200 a medium cave, and when we are above 200 square meter, that starts to be a large facility, it's large cave. A cave or a drying room or whatever the process is. Also, a small room will be under 3 meter high. 3 to 5 meters starts to be a medium height, and above 5 meter that starts to be pretty high, so normally a larger area. The parameters to control in a cheese cave, of course, temperature and the hygrometry, the humidity. That's the most simple, I would say, to control. After other parameters to be controlled are the air velocity, the homogeneity throughout the room, throughout the space, the cleanability, and for some type of cheese, we even need to control the gas concentration, so the oxygen, the dioxide, and the ammonia level in the rooms, in the aging room. And because we work in the food industry, of course, we have to pay attention to cleanliness, cleanability. Everything has to be clean, 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 and clean. When a cave is too large, sometimes it's funny, we go in, we visit the facilities, and either the cave or the draining room, you'll have just a crate or a few cheeses in a large room. And sometimes it's the other way around. You enter the room, you can't even go inside the room. It's so filled up with cheese, it's overcrowded of cheese. So both cases are bad. If it's too large, it's hard to keep the humidity level. It's sometimes hard to understand, but that's a fact. An empty cave is a dry cave, and that's a big problem with an empty room. And when it's too small and too crowded, then you have bad air circulation. There is uneven airflow. In some areas too fast, in some areas no airflow at all. The cheeses can't breathe. Why is it important to what is the concern with drying and aging spaces? We need to maintain homogeneity. That's a key to reduce standard deviations. and minimize your product loss. And of course, when you do all that, you will increase your profitability. I'm sure everybody's interested in making some money. So homogeneity is really one of the key. So making a parenthesis, I was talking about large spaces. What is the difference between large space and a small one? Well, you have the distance. You have the distance, of course, that are greater. And when a product is far from the air distribution system, normally you're going to have some ductwork, whether it's textile duct or something else. You're going to have a distribution system. So if there is a large distance, the air will only have a certain reach, maybe 6, 7, 10 meters for the most. So there is a point when cheeses that are too far, you can't reach them. And then vertical distance, this creates stratification, temperature stratification. We can see a small drawing here, but it's more with a static system. But just to give an example, you see on a 5-meter room, you can have as much as like 6 degrees difference between the bottom and the top. So you can imagine if you have a cheese in a room like that, you can imagine that the cheese on the lower shelves will not age the same way than the cheese that is on the top of the shelves. So of course you can't have homogeneity. So be careful with large spaces. So here you have some pictures that show this kind of large spaces. You can see that if you want every cheeses in that huge space to have the same properties, you have to make sure they're exposed to the same temperature, the same moisture level, the same air velocity. On the left side, it's an aging room, as you can see, and on the right side is a curing or drying room. So in this kind of process, you'll have cheese, for example, pressed cheese. It comes in the cave or in the curing room with let's say 38% moisture. You want to bring it down to 32% moisture. What will take this moisture away? It's the airflow. So you need to keep a precise air velocity on the cheese. We know by experience that if the air velocity is below 0.5 meter per second, there's going to be no curing. There's going to be no drying. When you do an aging room, you have two main technologies. You have static cooling and you have ventilated cooling or heating. So to reduce the risk of stratification, we use forced ventilation for large spaces. The static cooling is really working if you have a small facility, because in static cooling you will have a lot of temperature differential between the top and the bottom of your cave, between the up and down. So static cooling doesn't work for large facilities. You need to allow space for air circulation. So normally we don't put cheese on the upper shelves. We give normally at least 80 centimeters between the air duct and the upper shelves, and keep 60 centimeters between the walls and the cheese racks for the air circulation. So here is a small draft, an example of how it works. For example, air distribution. The air goes down and goes back through the alleys to the system. Now, big volume don't necessarily mean big cooling or heating capacity, but it can mean a big airflow to maintain a minimum mixing rate. In cheese caves or in curing rooms, drying room, we need to keep a certain mixing rate. It can be 15 volumes per hour, it can be 20 volumes per hour, it can be 30 volumes per hour, but this is normally a fixed volume depending on the cheese that you have and the process of the room. We know there is a mixing rate. Now, because it's not because the room is 10 times bigger and you have 10 times more cheese that the capacity that you need is 10 times more. Maybe it's going to be only 5 times. So sometimes you need an equipment that is not big in terms of cooling coil size, but you still need to keep this mixing rate. So we put additional fans to increase the mixing rate. So this is an important detail also in design, and this is even particularly true for curing and drying rooms, because I was telling you that there the velocity is very important, because it's the air velocity that will take the moisture away from your cheese. So this is something to be very careful in curing and drying rooms. If you have a wrong air distribution, for example, if you have a medium or high-rise facility and you have an equipment that is suspended on the roof, so you see the air is coming from the top, the air is returning on the top, everything is happening on the top of on the ceiling, if you want, and the cheese that will be on the lower part, where they won't see any airflow, they will not be exposed to a good air treatment. So you have a risk of that cheese don't get air, and you have a risk for development of pathogen, microorganisms, and bacteria in the dead zones, in the lower shelves. Now, for large caves, what we like to do is to have a distribution from the top and return on the lower part. Like that, we force the air to go from up to down and have a better exposure of all the cheeses to this air that we bring in the cave. So here are some pictures showing vertical duct. Again, to increase the mixing rate and to reduce the risk of air stratification. And sometimes it's not even enough. So we even use additional fans, the stratification fan that will take the air from the top of the room and bring it down. In some cases, when we have to really guarantee the efficiency and especially the drying of the cheese, we will use digital simulation that we call also computational fluid dynamics, CFD. So of course now there is more and more, the computers are getting more and more powerful. We have very precise results. So it can help to design spaces. It can help also to solve issues in existing spaces. So we can see visualization of temperature gradients. We can see also the air velocity throughout the space. We can, as I say, use that to guarantee the results of our system. For example, here a cave, a large cave. So we have to draw, of course, in detail all the cheese, all the air socs, the air diffusion duct, all the details, and then we run it in the computer, and we can have, for example, this kind of image. So here you can see on the left-hand side the scale. We go from, in dark blue, 0 meter per second, so no air velocity. No air velocity means no air circulation, and at 2 meter per second on top. So that's a very high velocity. So in that case, you see in the corners, we have very high velocity in the corners of the room, on the floor, and lots of areas with areas, seems to be area with low velocity. So we can change the scale. We put now the scales 0 to 0.3 meter per second. So like that, we can re-highlight what we want to see. I was talking about 0.3, 0.5 meter per second. That's the threshold. When we go below that speed, we know that the areas are reconsidered as dead zones. So here we can see, basically, you see these triangles. You can see these dark blue areas and light blue. So here we have 0.0 something, 0.1. There is no air velocity. So the cheeses that are in those areas, they will not age. They will not age properly. There might be some, moisture build. There are microenvironments, and as I said earlier, pathogen bacterial growth. So here there is probably a risk that they have issues with the aging of the cheeses in those areas. In the dead zone, there will be little to no air movements. Risk for these spaces to be either too dry, too humid, too warm. Risk for development of microorganisms, especially for blue vein cheeses, that is exothermic. it's a exothermic. It means it's a chemical reaction that creates heat. Bad aging for the cheeses in these areas. And for curing and drying process, as I said, on top of controlling the temperature and humidity, the air velocity is even more important because it's used to carry the moisture away. So here we did the same thing with a curing room, and where the client actually who had a problem in curing, and he even had shelves where he was not putting any cheese because he knew that he had to cure in 40 days, and in those some spaces he could leave it 60 days, 80 days, and it was still too humid. You know, the moisture content would just not drop. So we drew the cave again. We made this CFD, and same thing. We put the scale to what we are looking at, meaning 0.3, 0.5 meter per second, and here we could see the dead zones and the areas that we identified with the computer. When we talked with the cheesemaker, then he confirmed that was the areas where he was not putting any cheese because he knew that there was no curing happening. So when you know that, after you can do the other way around. You're like, okay, now I know the diffusion I have, I know where are the problems. So then you can tweak on the computer your airflow, and until you find a pattern that gives you a good air diffusion. So it can be used, as I said, to find out issues, to highlight the problems, and of course it also helps you to design something that is going to work. So of course this makes quality issues and eventually cheese that is not good for retail. So again, we come back to the profitability. Sometimes a digital, this is a pretty large facility. As you saw the pictures, there are thousands of cheeses. So it's important for them. A digital simulation like that can be a small investment compared to the amount of cheese they can lose. You know, so sometimes you have to see the investment versus the return on investment. The air is the medium in a cheese cave or curing room that keeps the temperature and humidity to set point. It carries the extra moisture away. It participates to the development of the flavor and the texture. Controlling the air movement is not easy, especially in large spaces, but it's critical. Voilà, so the advantages of a proper air treatment: regularity in the quality of your production, reduction of standard deviations, reduction of risk for airborne disease, reduction of production loss. You increase the lifetime of your cheeses or the shelf life, a reduction of the need of preservatives, and less labor intensive. I say less labor intensive because we see a lot of cheesemakers. So they take the cheese, they leave it a couple of days in the corner left below here, and then after a couple of days they move it up here because they know if they want to have something homogeneous, they have to turn the cheese around. So they spend so much time moving their cheese around, and that's not where their added value is. They're not movers. They're not supposed to be movers. So a few pictures of cheese caves, but probably all know how it looks like. So with this air distribution, duct or no duct, depending on the process. So I'm gonna give back the hand to Jennifer.
Okay, thanks very much, Michael. Are you right now to share? So please just note your questions that you want to ask David and type them in at the end.
Okay, can you see my screen okay? Okay.
Yes, Dave. Yes. Yeah.
Can you hear me all right? Can you see my screen okay? Jennifer? Hello?
Oh, yes. Yeah, I can. That's
Yes.
right.
Hi. Great. Okay. I'm going to get going here. My name's Michael Kalish. It's a pleasure to be here, and thank you, David, for that pleasant presentation. I like the idea of not being a mover also. So today I'm gonna just sort of run you through some ideas on how to approach troubleshooting when you're seeing issues during the aging process. A lot of people feel like all their answers lie in controlling the cheese when it's aging, and some people see a lot of problems because of what they do during aging. It's very difficult to discern out what the causes are. So you may have at different times in your cheese making room sort of scratch your head and thought, well, like, am I not thinking of a specific variable? Is there something I haven't thought about yet? And there's a huge list of variables that can impact your cheese. And just like with foodborne illness, we see the problem at the retail level. With cheese, you'll tend to find the problems during aging. And so whether or not you've invested in appropriate equipment for aging cheese, there's still that possibility that you'll see a problem, and the attribution is going to really depend on how well you can go back and see what might have happened. So this is just a little mind map where we have milk quality issues coming from these kinds of variables, whether they be animal stress and health, just the biochemical composition of the milk itself, or other ingredients you might have added. That could include an excessive microbial load or the absence of one. For cheese making, I first and foremost think about hygiene and sanitation, as David was mentioning. But then there are also all these other variables like pH or fermentation. When we talk about pH, it could be you arrived at the right pH, just it took too long, or it didn't take long enough, because you might have had excessive drying or insufficient drying during that time period. So there's a lot of different variables, and today we're going to take a look at how to systematically address those for the purpose of troubleshooting. You can see down here in Affinage, and I'm going to show you a lot of photos that give you some examples here. But from how often you're brushing, how intensely you're brushing, those things can have a big impact on the finished product. And so can air, as David's been talking about, and then just how you tend to space out your product in the aging room. We'll take a look at what that looks like. So these are the 4 fundamental steps that I recommend to cheese making businesses when they start approaching troubleshooting. First, identify those weaknesses across your facility. A lot of facilities are old. You may have not built the facility from the ground up. Maybe you moved in, and so you inherited some design issues. But that shouldn't make you stop considering, acknowledging the different weaknesses you have. I like first starting with flow. What's my flow of milk or curd? What are my flow of other ingredients? And how do my chemicals move through my plant? You might also want to consider all the different ways your staff have to get to the bathroom. How do they reach the office? Where are the opportunities where we see hands and wheels potentially contaminating rooms and ultimately food contact surfaces? It's much easier to address these poor hygiene issues through sanitation than it is through massive cleanup of your aging room. So starting here is definitely one of the places I recommend starting. And when you identify high-risk rooms, consider what kind of practices you're going to be encouraging in those rooms. Those weaknesses will be highlighted there. So I really do you don't need a fancy software to lay out your facility. You can draw it down on a piece of paper, and you don't have to draw the equipment. We're just looking for flow, which takes me to my next step, which is establishing specifications. So once you have a flow diagram, it sort of breaks out all the individual steps for your processing. That's the place where you can start focusing on the specifications for your works in progress. So when you're renting to when you're aging, you should be expecting a specific weight loss over the course of that time at each individual step. So when I say specification, you can take note of what the optimal weight loss is across time for a single lot. And then you can try and replicate that. But you'll notice over time with each season, what resulted in a desirable product will have some variability. So we're not looking for a specific value. We're looking for a range, and it could be seasonally sensitive. So when I talk about weight loss, I'm talking about yield. And it's not uncommon for manufacturers in France to weigh their product as it moves from the draining table to the drying room and finally to the final room for aging. Shape and texture, rind, if you haven't already fleshed out these work in progress specifications, it'll be fairly difficult to see where things go wrong. Cheesemakers are pretty well known for having good intuitions, so maybe you don't have to write it down, but at least have a concept for yourself what it means to be a work in progress at each individual step. And next is finished product specifications. So the important thing here is to be able to relate back to the WIP specs, how well things turned out for you in terms of flavor and aroma, and then also all of these other parameters above. So once you have your specifications, the next part to having an effective approach system for troubleshooting is keeping records. It's a way that you can start establishing trends and making connections between things. This is, you know, any office involved in investigations will try and establish a means to collect data and then try and establish relationships between the data so they can make data-driven decisions. So this is where it starts with assessing the issue. Here I'd be calling out the product and the lot number, the date or the time or shift that the issue was observed, and then during what process step the issue became noticeable. It may have had its cause far before, but this is a really important thing to see, because as we note this, we'll be able to at least see a pattern of appearance. Next is we want to identify whether or not these defects are localized, if they're skewed. So if maybe there's a large percentage of product that's affected, but never all of it, or if it's evenly distributed. And I like having just a little table for me to be able to sort of call out right away, you know, what the problem is. Am I seeing significant weight loss in a small percentage of my products towards the window, towards the wall, towards the center of the room? Am I seeing some defect shapes and textures in my product? Is that skewed? Is that localized? Is it evenly distributed? We'll see in a little bit why that's important. And that's within a lot, but you should also be looking across lots. Is this something that's just happening in the fall? Is it happening intermittently across the year? Or is it a chronic problem, right? If it's a chronic problem, you probably don't have any time to write this down. You're calling for help. But this is a good way of essentially establishing a spec for your quality issues. Next is describing the issue and its frequency. If you can attach a picture, great. And then checking the variables that you've investigated. You know, it's especially when you have more than one employee in a cheese room. And people, you know, we have rollover in the dairy industry. It's very easy to lose a tremendous amount of knowledge when it's siloed in a specific individual that has a lot of experience. We have a lot of people retiring from university extensions here in the United States, and you know, they're taking with them a lot of information, like a experienced cheesemaker might. So documenting these quality issues and getting them well defined is important for sort of the future of your operation as you look forward, and especially towards hiring and offsetting some of the work. For controls that have been implemented, it's also a good idea to write down what it is that you've done and take some ownership. So this is what I call establishing a specification for a quality issue. And in this case, it's issue 001. And the reason why I like establishing this sort of specification is so I can trend. So over the course of the year, I can say, hey, well, issue 001 popped up quite a bit this year. This is a very simple table. You could draw it in the sand, or you could write it on a piece of paper. But if you were to express it graphically, you could see the interrelationship between the defects over time and over seasons. So that's why I really like establishing what the problem is, documenting it, and then putting it into perspective as we see across the year and multiple years, problems coming and going in our facility. Oftentimes, smaller problems can be good indicators for lapses in sanitation or processing mistakes, and can help indicate that, you know, before there's a bigger problem to come. Okay, so now for some cheese pictures. I'm just going to focus on the fundamentals here. We'll start looking at milking and work our way down towards aging. This happens to be a real cave that I worked in Italy back in 2008. I was surprised. There's some good stories here. A great example of very, very poor hygiene, very, very rustic cheeses, and a tremendous number of problems. So this was really just for entertainment. I'm going to move along. I did have an opportunity to work with Mons Fromager Affinage. They're a cheese aging enterprise in France, and a wonderful one at that. And they worked with, gosh, just dozens and dozens of different suppliers. So I managed I managed their train tunnel. It was 200 meters long, 60 tons of cheese at a time being aged. And we had over 30 different types of cheese, I believe, in that tunnel at one time, and over 100 different cheeses across their enterprise. So quality assurance was a real big deal to the company. I had an opportunity to go visit a number of their producers, so I'm going to run you through a few pictures of those. Here's a couple of cases where we have a very small operation. This is a milking parlor. You can see he's sweeping manually. Whenever he'd sweep, he'd push a huge number of spores into the air. And so this was always practiced after milking, not before milking. And ventilation in that room actually had a big impact on the microbial load of the milk. Grains also carry with them a lot of dust and in them spores. This happens to be a facility design, by the way, that I'm just going to reference. I'm just going to show you real quick sort of how things move. Milk comes from the milking parlor over here through into the bulk tank. From the bulk tank, which is outside of this little door here, the milk pours into these mobile units, which contain the milk that will be coagulating. And then it will be moving through the renneting room into the draining room, where the curd is ladled into molds. And from there, the molds drain and then are subject to drying before then moved to an aging room. They're then packaged, moved into a refrigerator, and shipped out. So this is a really lovely design. I actually took it off of the Loire Valley. They have some resources there for local cheesemakers, and then I made some adjustments so I make it exactly how I wanted. But this is an example of unidirectional flow for a facility. So we talked about weaknesses in the facility. This one doesn't have too many. So I'm going to keep moving down here in examples. So draining, here are a couple different approaches to draining where, you know, uniformity is what we're looking for, uniform treatment. And that's what David was talking about earlier, was how do we arrive at homogeneity? When you don't achieve homogeneity, or you don't apply controls uniformly to your cheese at each step, it makes it more and more difficult to arrive at a homogeneous finished product in the aging room. So before you start looking at what went wrong with your aging equipment, you should definitely consider where you can achieve homogeneity earlier on in the process. And you know, obviously the cheese on this side likely will drain a little better than some maybe towards the bottom down here. So the nature of cheese making is not every cheese is going to be treated the same, but the way that you can mix it up is by turning these carts, for example, or changing the order of them. But ultimately, with very small facilities, it's going to be difficult to treat everything so uniformly. These guys were beautiful. This is a blue cheese production. They're able to churn these by hand, all at once. So they're treated actually with great consistency. These, on the other hand, these are being pushed together laterally. And as a result, there was a little more pressure. There were some that would be pinched, and so we'd find some small issues around the exterior of the cheese where the curd would pinch, and so moisture couldn't get out of it so easily. And we'd experience some variable mold growth on the surfaces of these cheese during the aging process. So this was a great example of where we might be able to communicate with the producer to solve problems we were experiencing in the aging room. These are some lactic cheeses. Moisture was being absorbed underneath these cheeses with these absorbent mats. These actually came out incredibly uniform, but it was because we were changing out those papers so often. It was so important in this room that the ones on bottom be moved to the top later on, and that the carts be turned every so often. Obviously, if you have better equipment in your aging room or in your cheese aging facility that makes airflow more uniform, you won't have to be this mover, as David said, or this person who is constantly making up for the failings in their technology. But it is a place to start until you can make that investment. This is a drying room where the air was coming out of this thing up here, and it was turned around. So it was actually hitting the wall. And from the wall, then come back and run along the wall until it hit the door, and it would turn back around and go down the center. Again, a very rustic sort of approach to drying, not entirely uniform, which meant that people managing this room would have to do a lot of footwork to keep the racks turned around and moved in different positions. It was, by Mons, it was, I thought, an incredible feat. He had achieved such high quality with the system, despite any kind of hurdles he had with his technology. He really made it work. So very hard to reproduce. I'd say the hardest thing to reproduce is how loaded this room is with mold, which was desirable for the surface of these cheeses. And I think a big trick of that was keeping the room full, which is an interesting variable, which we're actually going to talk about in just a moment. So these are just some examples of aging rooms, theoretical and otherwise. When we're looking at treating things uniformly, we're looking at even vertical spacing. These are just a few different examples where we have fairly uniform vertical spacing. That's not totally uncommon. What's more or less common is lateral spacing. How do you space it out laterally to ensure a uniform airflow around a product? There are cases where you will be putting them very close to one another. Here you can see we have some bars. They're incredibly close to one another. And the reason was because they're actually fairly dry, and we didn't want them to dry out any further. So, do you manage the humidity of the room or the ventilation of the room, or do you play around with lateral spacing? The answer should be all the above, if possible. Here you can see we have quite a wet print from the bottom of this cheese. So changing out the paper is another thing that can be done to accomplish uniform treatment of cheese across lots and over time. Okay, so just a few examples of lateral spacing. Here we have some examples of different types of shelving, some better than others. We have some plastic ones here that were fairly sort of makeshift. It was not an ideal situation, and there was a lot of, wherever the cheese pressed against this plastic bar here, it would be trapped and modify really how that surface was going to respire and cultivate mold. Here we have wood where it's covering up the surfaces, so really detrimental to the flow of air. But in this case, they were compensating for too much ventilation in the room by closing up the cheese. When cheese is tightly fitting a shelf, it can produce heat, some more than others. Blue cheese is pretty famous for producing a lot of heat. So these sort of lactic mold-ripened cheeses. So that's something to consider. I think David has just awesome photos illustrating that. But in this case, these cheese agers were really just trying to accommodate for problems they had seen over time by manipulating the airflow themselves. So introducing hurdles as opposed to, again, investing in more advanced, more sophisticated technology. There's a breaking point. After a while, you have so much cheese or so many problems with yield that you invest in greater technology, but some people manage to juggle it. So this is just a little photo of where the cheese starts and where it ends. This is a cheese that they never turned. So they were literally leaving it out in the drying room and letting it age over time, developing this rind until finally the bottom could be dried out. And again, uniform spacing, lateral and vertical. In this case, it was a little tray that fit into a sort of a baker's rack, mobile baker's rack. And they're using straw here. I don't recommend that really for you guys because it does have a history of hygiene problems, a little more difficult to control, especially if you don't have control over the supply of the straw. So it's typically not really acceptable in food safety circles. But here, Mullins is a special place. They were able to accomplish some incredible quality objectives. And then there's handling. I think really identifying like how often people touch things, who touch them, and how often. Those things are variables that can really be either good or problematic. Hands are definitely the #1 vector for contamination with cheese, as far as I'm concerned. This was that place where I was able to take these photos, Mons Fromager in France, Académie Opus Capsus. So really quickly, I know I'm kind of running out of time here. I wanted to just show you an example of where during the aging process, we arrive with some fissures. I'm going to use just pressed, not cooked cheese as an example. This, obviously things went terribly wrong. So when we find these sorts of fissures in cheese, which in France they call laneurs, what's the origin? Was it something I did during aging? It could have been, but it could have been a number of other things. It could have been a combination of things. So these are a few different types of fissures. We have a closed fissure. This is typically, really tiny, 0 to 1 millimeters. You can really only find it through a core sample. So if you're used to tapping your cheese for sounds, at best bet, you'll find something greater than 1 millimeter. We call it an open fissure. And then we have a tip of a fissure. It might evolve into something where, it might become a larger problem later on in the process, but something discovered early on. An open fissure, I don't know if you've ever cut into a piece of confit, for example. It's not a not cooked cheese, it's pressed cooked cheese, but if you ever cut into confit and it just splits apart, you didn't see the fissure, but it existed there. Those are cases where very small fissures happen, and not a tremendous defect, but obviously the goal is not to arrive at this souffleur, this blown wheel of cheese here where there's a visual defect on the face. There are a number of different reasons where you can see these fissures occur or become a problem. It could be the milk quality. You could have a significant microbial fermentation where you're having huge amounts of gas produced. The CO2 is an example of gas that can move through the cheese. If the rind is too dry, it could be trapped inside, and with enough pressure, it will bust open the paste, depending how firm the paste is. So CO2 can be a problem. Hydrogen gas, that's going to be a problem that likely is going to be associated with bitterness spiciness, and a load of other problems. We'll take a look at what that looks like in a second. On the manufacturing side, we can have draining issues. Sometimes when the curd fails to acidify, we can fail to exude whey during the draining process. If the fermentation runs away and is too strong, we find the cheese become a little brittle because it sort of makes it lose its calcium. And as a result, the press is not going to be as effective as intended. And so for all these reasons, we might find excessive moisture trapped in the curd, and that could result in some additional fermentation. Also, if you have poor curd cohesion in the mold, that also can end up resulting in some mechanical holes or fissures that are exacerbated by the production of gas. So it's not really until we get to the aging side here, we've already gone through quite a few problems associated with fissures. The big one with aging is a high temperature. Increasing the temperature in an aging room can help accelerate the aging process, where we can, arrive at a more tasty and aromatic product quicker. But at the same time, if we have any problems from milk quality or manufacturing, we can see undesirable microbes produce an unwanted effect on the cheese. We can also experience some physicochemical changes in the cheese that will result in this fragile texture of the cheese that's more susceptible to busting open into fissures. So typically, we don't see these long-aged cheeses aged above 12 degrees Celsius. That's kind of the breaking point in my experience, where we start seeing quality problems. Doesn't mean you can't age above that. It just means that you're taking a greater risk with the number of cheeses you're aging. This is shared. There's an organization, I kind of provided a little picture of them down here, where they put together an entire sort of, they call it a fiche technique, where they outline sort of how you can go about troubleshooting when you experience things like holes, or in this case, fissures. In this case, I just provided this, and you'll have a copy of this for yourselves, but where there's evidence of bloating, where we have a dry rind, fissures that are localized on the face or in a pocket in the cheese, or maybe on a side or just the center of the cheese, you can go ahead and start there and say, well, is the cheese bloated or not bloated? The blue flame test, hydrogen burns blue. So if you core a cheese and you have a lighter next to it, you can identify hydrogen gas with a little blue flame test. Just light it up and thing turns blue. If it's carbon dioxide, we're not going to see that kind of problem. Carbon dioxide is a popular byproduct of heterofermentive bacteria. So, you can follow these sort of pathways into figuring out, well, what happened, and from there we can go back and try and troubleshoot. So I do recommend looking at it. It is in French, so we may have to have a little translation going. I did translate this one for you guys. But this is what it looks like, and they're great diagrams and pictures. I definitely recommend consulting it, and also this group. They're fantastic and put together a lot of great French resources. So a little summary of what we've discussed is: first, identify the facility weaknesses. Next, establish those specifications for both work in progress and finished product. So we talked about weighing the product as it moves through its different processing steps, for example, so we can identify target yields. Third was to assess, evaluate, and control, essentially document those things so that you can go ahead and trend. And that's my presentation. So any questions? We're going to turn to the chat.
There was a question if the air is normally HEPA filtered. So yes and no. There is two air systems in facilities. You have the recirculated air, so what treats the room in temperature, humidity, etc. This is just a recirculated air. There is no filtration. Then you have the makeup air, because like Michael was saying, you need to look at the clean area and the not so clean area. And of course, you will keep what we call airflow management. So we keep the air moving from the high pressure area, which are the more sensitive area, to the less sensitive area. So the HEPA, the makeup air or the fresh air, yes, it has to be HEPA filtered. Is the air for drying normally dehumidified? Yes, we use a cooling coil with cold water. It's very important to use cold water in our opinion, and not direct expansion, because we can really control the temperature of the coil versus the dew point of the room, so we can control the exact dehumidification of the room. And when we control the dehumidification of the room, we control the dehumidification of the cheese and the amount of water that will pump out from the cheese. It's very easy. You have 500 kilo of cheese. You want to take off 6% of moisture within 30 days. Well, you do the math. You know exactly how many kilo or pounds or liter of water you have to pump out, and that's what your coil has to pump out. There's with strategic air control, there is no need to turn the cheese. So I say, no, you always need to turn the cheese, although in the presentation of Michael, there was this pyramidal cheeses that he said that don't turn around. So it's the exception that confirms the rule. But normally, no, even though you have a good air treatment, you normally still have to turn your cheese, you brush them, you do whatever you have to do, but you still have to normally move them around.
In the mobile plastic renneting tank shown, how was the temperature controlled for culturing?
Yeah, I think it was heated like actually any room might. I don't believe they were filtering. I believe they had a light filter on the air coming in, and they had maybe a heating coil or something of that sort. I don't think it was too sophisticated. But I suppose I really want to just highlight that it was a very, very small renneting room. And so they were able to control the heat in there very, very well, and not have that heat affect the warmth of the coolness of the draining room, which was conversely a little bit cooler. So that was the purpose of the mobile plastic renneting tank, that it could be wheeled from a warm room to a slightly less warm room.
In the next question, is unwanted mold a common problem for commercial aging and drying? If so, how do you manage it?
Yeah. Absolutely, it is a huge problem, and there are two ways that people go about. A couple of different ways that people go about managing it. One is that you keep things as clean as possible, and you filter the air, and you control who goes in and who goes out, because you can bring in undesirable microbes, or mold, or yeast in your hair, on your skin, and in your clothes. So, trying to keep it as hygienic as possible and controlling access to that room, to the aging room or drying room or facility as a whole is a way that people are able to manage it. And David mentioned air management, keeping positive air pressure so that clean air is constantly being pushed in at a greater rate than air coming from the outside elsewhere. So, you're constantly getting this turnover in high quality air, filtered air. That's a good way of managing it. But we've seen in less sophisticated, and I say less sophisticated like it's bad, but it's not. It's just where people had less means, charging a room with high levels of mold is another way of doing it. Mold ultimately is in a competition. Whether you're making an industrial camembert or one of those pyramidal cheeses, Penicillium candidum grows very slow compared to Geotrichum candidum. And so you'll sometimes see people decide that they'll use a cocktail, or they'll use Geotrichum candidum to colonize the surface of the cheese very quickly. So it's inaccessible to undesirable molds, but can have a symbiotic relationship with things like Penicillium candidum. So you can get that nice white blanket and not experience those unwanted mold problems. But so those are two different approaches, and they can be used in tandem. And those are ones that we see consistently across the industry.
So for medium-sized cave, about 100 square meter, for alpine style cheese, is static cooling a viable option to look at, or is it better to work with airflow and a diffuser? So, well, I mean, for this kind of cheesecake, I would say both options are probably possible. Here, I think I would say it will probably depend on the height of your facility. If it's pretty low ceiling, you can probably go with a static cooling. If it's high ceiling, I would recommend a ventilated cooling. Again, with static system, it's always complicated to guarantee the homogeneity. So it's we're not very fond of in static cooling. Again, you have people like Mons who really master that technology because, of course, they have the experience. They are best affiner in France, so they can do pretty much whatever they want. But it's I mean, for sure, with a ventilated system, it's much easier to manage.
So Lynn has asked, for hard cheeses and internally ripened, if inevitably unwanted mold growth was observed, is it normally wiped down with brine or another technique? So maybe Michael, you asked that one.
Sure. And yeah, there are different ways you can knock back mold, but mold is something that on this earth was bound to survive. It is very difficult once there to knock back entirely. But, increasing the salt concentration on the surface is one way of doing it. And applying a brine will help also select for things that are more salt tolerant. If it happens to be the mold that's salt tolerant and more salt tolerant than anything else, you may be selecting more and more for it. But oftentimes, knocking back things with a brine is a common practice. And I've seen others, try and use diluted solutions of vinegar, but never with tremendous success. Really, there's not much of an alternative for having positive pressure equipment that you can clean inside and out, and a filter that you can replace, and then also turning over your product and clearing out the room. If it's a significant problem that presenting an existential issue for your creamery, a deep clean like that and selection of an investment in equipment you can use to maintain things cleanly would be sort of the alternative I'd encourage. But other than that, yeah, if it's a hard cheese, you can wipe it down with the brine. Just note what happens over time. If you're selecting more and more for these salt-tolerant microbes, you may want to pursue another course of action.
I'd like to ask, what airflow devices, David, would you recommend for small cheese facilities? And I know Emma has just dropped off, but a lot of these smaller cheese makers who end up with it, they start with a small affinage room and they end up like Kim, you start to produce more and more cheese. Mm-hmm. Airflow becomes much more of an issue. So what would you recommend there?
Well, in terms of equipment?
Yes, yeah.
So of course the equipment, like I was saying in my presentation, it's important to have equipment in stainless steel. So it's easy to wash and equipment that are accessible. You need, we recommend also the diffusion with a textile duct. The textile duct, I don't know if you've seen it, if you heard about it, it's made of a fabric, of cloth, and it was actually invented for the food industry because, the problem with metal duct, you can go inside, you can clean them. So a fabric duct, you can take it out, put it in your washing machine, put some detergent, and kill all the bacteria, and you put it back, it's nice and clean. And the air treatment system, same thing, it has to be fully openable, accessible, so you can, gun form inside. Of course, the washing is different if you're in a production area or in a cave. In a cave, as Michael was saying, you try to get actually some mold inside that participate to the aging of your cheese. So you don't want to clean that every day or every week or even every month. Some people just clean their equipment every, like once a year or something. It's not easy. I mean, you have to remove all the cheese from your cave. It's not easy equipment to wash. In other areas, maybe in manufacturing or salting or what, you can, you basically have different batch every day, so it's easier to plan for cleaning. But yeah, the rule is really to use stainless steel. You know that in our industry the milk seems to be something nice and soft, but it's actually very aggressive. Anything that is not stainless steel will not survive in a cheese facility. All your vats, your tools, your tables, I'm sure everything is in stainless steel, because otherwise for a fact that it's going to rust. But it's the same for the air treatment equipment. Whatever you put, if it's not stainless steel, eventually after 1 to 2 years maximum, it's going to rust.